Welcome to today's chemistry classes. So in the past three parts we have seen about the valence bond theory, its application for a given coordination complex, and what were the difficulties in order to explain the coordination compound with the help of V beta. There is nothing but the limitations we have learnt. So due to some of the limitations of valence bond theory, since it was not at all explaining properly the bonding, how it is taking place, and or even the magnetic property and all those things. Okay, those students who have not yet watched the limitations of PBT, the link is in the description. Go and watch it once, and then you will understand that yes, what is necessary, why we need to learn the crystal field theory. Because see here, due to the limitations of the VBT itself, the crystal field theory came into existence. In order to explain some of the limitations of VBT, yes, we required another theory in order to explain the shortcomings of VBT, and that thing was given with the help of a new theory called as a crystal field theory. So this crystal field theory was introduced by the Bethe and the Welk. So Bethe and the Welk were the two scientists who introduced the crystal field theory for us. So the main perspective of this crystal field theory was, in order to overcome the limitations of VBT, that is nothing but the VBT. In VBT, it never discloses anything about the color of the complex, while C.F.T explains the color property. C.F.T explains why coordination complexes are showing some of the colors. In the same way, VBT didn't explain the bonding properly. Okay, it was just a pictorial way, so only we said that VBT is only qualitative in nature. So on that note, the C.F.T also explains the bonding between the central metal ion and the ligand in a nicer way. In the same way, crystal field theory explains the magnetic property. Here one point should be remembered is the magnetic property which was discussed by the crystal field theory was exact number. Exactly the experimental and theoretical values were almost exactly, they were matching. So on that note, CFT is having a greater things in order to explain the coordination complex. So one thing is the color, second thing is explain the bonding also, and along with that the one property which was not explained by the VBT was explained by the CFT, that was the magnetic property of a given coordination complex. Here the exact matching was taking place with the help of CFT when we calculated the magnetic momentums. So in the same way, the CFT also explains the interaction of the d orbital. See here, in the complexation process, yes, the d orbitals are involved. As we all know, the metal d orbitals are involved. See here, according to the VBT, the hybridization and all those things were there, but according to CFT, yes, there is a splitting of d orbital takes place. The splitting of d orbital will takes place. On that note, see here, another thing to be remembered is CFT never explains about the hybridization. So in the whole crystal field theory, you won't see the hybridization things, that is hybridization properties like sp3, sp2, dsp2, all those things are not discussed here in CFT. Only the VBT explains about hybridization, but CFT is independent of hybridization, but rather it explains all these four properties, that is interaction of d orbital, magnetic property, a bonding, and also the color property of the coordination complex. So in order to study this important theory, that is crystal field theory, there are some assumptions to be done. In that, the first assumption is, it assumes that the ligand and central metal atom or the ion interaction to be purely ionic, see here, and not covalent. But according to the VBT, yes, the overlapping of the orbitals were taking place, and that remembers about the covalent nature. But according to CFT, the central metal is there, ion is there, yes, the bonding is taking place, and that bonding is purely ionic in nature. Remember one thing, this is a very important thing here. Okay, the interaction between the ligand and the central metal atom or the ion is it is purely ionic and not covalent. That means this model is also called as the electrostatic model. Remember one thing. So even the CFT is also called as what? The electrostatic model. Why? Because there is the interaction between the ligand and the central metal atom is what? It's a purely ionic. One acts as a what? Cation, another acts as an anion. In between the positive and negatively charged ions, as we all know, there is what? Electrostatic force of attraction which will bind both the ions together. And for that reason, yes, the CFT is also called as what? The electrostatic model. And next thing is, yes, the ligands are considered, according to CFT, the ligands are of two types. One is the ionic ligand, another one is the what? The neutral ligand. Here ionic ligand is nothing but the what? An ionic ligand itself, because a ligand acts as a negatively charged particles here. Remember one thing, ligand acts as what? Negatively charged particle, because they are having the extra electrons to be donated to what? The central metal atom. So our hatra yenide extra electrons ide. For on that note, yes, the ligands are of two types. One is the ionic and second one is what? It's a neutral in nature. So ionic, for example, F minus Cl minus Cn minus, or any ligand which is having the negative charge over them are what? The ionic ligand. That means the anionic ligands. The one which acts as a neutral in nature comes under the neutral ligand, like ammonia, H2, etc. See here the ionic ligands to be considered as the point charges, while the neutral ligand is considered as the dipole. See here, the central metal atom is there, which is in the what? Which is in the cationic state. Why? Because all metals are having what? The deficiency of the what? Electron here in coordination complex. So they stay in what? M plus state, that is metal ion state. So for this M plus state, if there is what? A ionic ligand is there. If there is a ionic ligand is there, let me consider as what? L minus as what? A ionic ligand. L minus as a ionic ligand. So see here, so according to what? According to CFT, if there is a ionic ligand is there, the central metal atom acts as a positive point charge, and the ligand acts as what? A negative point charge. So in between the what? The positive point charge and the negative point charge, there is what? Electrostatic force of attraction. Electrostatic force of attraction. That is how a ligand is binded to what? The central metal ion here. So when to consider it as a point charges, when to consider these are the point charges, when it is the ligands comes under the consideration of ionic things, that is ionic ligands, like F minus, Cl minus. So here they act as what? A point charges, while each point is indicated with the help of what? Positive and negative, with respect to positive for the metal and negative for the what? Ligand. So in the same way, if the metal ion is present here, and if the ligand is a neutral one, if the ligand is what? A neutral one, then it is considered as what? A dipole. A dipole. As we all know, dipoles are also having what? Two opposite charges which are separated by a certain distance is called as what? A dipole. That means the negative terminal of the dipole, if you consider the negative terminal of the dipole, here is a positive, here is a negative thing. So the negative terminal of the dipole is directed towards the what? The central metal ion here. So for point charges, yes, there is a strong electrostatic force of attraction. Here when it comes to neutral ligands, it is considered as a dipole. Dipole again has two charges, one is positive charge and is what? Negative charge, which is separated by a certain distance, and that negative charge is directed towards the central metal atom or the ion. So this is how the interaction is to be what? Purely ionic. See here, positive, negative, negative, whether it may be what? Like whether the ligand may act as a point charge, or it may act as what? Or it may act as a dipole. Yes, there is an interaction between the what? The positive and the negative terminals here. One acts as a point charges, another acts as what? A dipole, the ligands. So in both these two cases, yes, it is what? Purely ionic in nature. It is what? Purely where is the duster? Yes, purely ionic in nature. Yes. So this was another assumption of the what? The CFT. And next one is the what? The CFT explains the what? The splitting of only d orbital. Remember one thing, this is one of the limitations of valence bond theory. And the limitation of the valence bond theory was about what? VBT doesn't explain about the what? The splitting of d orbitals in the complexation. See here, according to CFT, yes, the d orbitals, if you consider a d orbital 1, 2, 3, 4 and 5, if you consider a d orbital orbital, yes, see these metal d orbitals. These metal d orbitals are split up into two energy levels, will be split up into two energy levels. See here. So how many orbitals are there in d orbitals? That is 5 orbitals you can find. That is dxy, dyz, dzx, dx square minus y square and dz square. See here, all these 5d orbitals, are split into what? Different energies. One acts as a lower energy, another acts as what? Higher energy in the complexation. So this d orbital is split into what? Into two energy levels. But here the thing is what? It depends upon the what? The field also, whether it is a octahedral field or a what? Or it is a tetrahedral field. So this how the splitting will take place, what is the major, why the splitting is taking place, how come the how come these orbitals in which they are considered as a lower energy orbitals and higher energy orbitals, all these things will be learnt later. So now we are just only discussing about the assumptions. Yes, in the next part we will discuss about the splitting of the d orbital in a proper way. Why, how and which orbitals are acting as a higher energy level and lower energy level, we will see in the in the next part. Okay, now as of now let us consider that as in CFT, yes, it explains the the splitting of the d orbital, but the splitting depends upon the the crystal field here. So the splitting depends upon the the crystal field. All those things will be learnt in the next part. So as of now let us consider the assumption here, and the next assumption is the metal electrons see here. Okay, the metal electrons present in the d orbitals move farther away from the direction of the ligand. See, this is the very important assumption of crystal field theory. So why splitting anta nodidaga, yes, this is the main reason. See here, let me consider an example. A metal ion is there. Okay, yes, this metal ion is having what? It is having a d orbital. It is having what? A d orbital having an electron. It is also having what? An electron in it. Okay, an electron pair is there. Now the ligand is present here. This ligand is also having what? It is also having an electron pair. As we all know, according to the universal law, same charges repel each other, unlike charges attract each other, same charges repel each other. See here, for metal also, yes, the metal is having d orbitals. In that d orbitals there are some paired electrons are there are some unpaired electrons are there. Yes, very good sir. So here the thing is, when the ligand is approaching the central metal atom or the ion, so what is the major thing which is happening here? Here, for example, let me consider this as what? A d orbital if you consider here. So this d orbital electron and this ligand electron will be what? Repelled each other. That means there won't be bonding itself. There should be, in order to form a coordination complex, yes, there should be a bond between the central metal atom and the ligand. But what about here? Here, when the ligand approaches towards the metal ion, the repulsion is taking place here. Why? Because there are some electrons which are present in the d orbital will be repelled, will repulse the electrons which are donated by the ligands here. So here the very important thing takes place. That means these d orbitals of metal, see here, these d orbitals of metal will adjust now. See here, let me take this example only. Again the metal ion is there. So actually at first this is how the orientation of the d orbital was there. Now if you consider, if I place that orbital like this and if I place the ligand here now, okay, this is the same d orbital, okay, which is having an unpaired electron, and again the ligand is here. Now if you see here, even though there may be a slight repulsion is there because the electron clouds are there, no? So on that reason, yes, for some extent if you consider case 1 and case 2, if you consider case 1 and case 2, the repulsion is very greater here in case 1. Why? Because both the orbital and ligand are along the same direction. But here if you consider, the d orbital is adjusted itself now. It is moving far away from the what? From the direction of the what? The ligand here. That means yes, there is a chances of formation of the what? The bond here. Why? Because the repulsion is very less. So here, according to CFT, see here, the VBT didn't explain these things. So according to CFT, if there is a coordination complex which is going to be formed, in that case, the d orbitals of the metal, see here, the d orbitals of the metal are split up into what? Higher energy level and lower energy level. In the same way, the d orbitals are what? The d orbitals which are having some electrons in them. We are not at all talking about the empty orbitals here. We are talking about the what? The orbitals which are having some electron. So those orbitals will what? They move far away from the direction of the ligand from which it is going to bind the central metal atom or the ion. So this is a very, very important case. Okay. So on that note, this was a case here. See, the metal electrons are present in the d orbital. So in that metal ion, if there are any electrons are present in d orbital, that orbital will move far away from the direction of the what? The ligand which is going to donate the electron to the central metal atom or the ion here. So this was the case that. So you can see here in case 1 the repulsion is more, but in case 2 the repulsion is less or negligible, you can call it as. Yes, this is the direction of the what? The ligand which is going to bind the central metal atom or the ion. So here if you can say this is M plus, this is L minus, that means what? Again the same thing, see here. It assumes that what? The interactions are purely ionic here. The interactions are what? Purely ionic when it comes to what? CFT. And next assumption is very simple thing. Actually the CFT is very beautiful, okay? We will explain it in the next part. So these are just the assumptions. Okay, and the next thing is the number of the ligands and its arrangement around the central metal atom will determine the crystal field. So since we are learning about the what? The crystal field theory, for example, see here, we are considering a central metal ion. If you place that central metal atom or the ion in a what? In a crystal field. In a crystal field. So this is a crystal field, the spherical crystal field we are taking here. So for example, let us consider some of the ligands here. Some of the ligands. Let me erase this one. So now the direction of the ligand is like this one. This is the direction of the what? The ligands which are present around the what? The central metal atom or the ion here. See here, the number of the ligand. How many number of ligands are there? 1, 2, 3, 4, 5, 6 ligands are there. So the number of ligands and its arrangement around this central metal atom. Which type of arrangement it is? Octahedral arrangement. As we all know, okay, in VBT we have learnt, okay, octahedral arrangement it is, yes, arrangement it is. So will determine the what? The crystal field. Very, very important. See here. So the crystal field, if you are seeing here, so that crystal field depends upon the what? The number of the ligand and its arrangement around the central metal atom or the ion. So for each different number of ligands and arrangement, yes, the crystal field will be having what? Different determinations like the splitting and all those things. For each type of arrangement of the ligands and the number of ligands, you can see the what? The different studies for each of the crystal field things here. Why? Because it depends upon the what? The crystal field depends upon the number of the ligands and the arrangement of these ligands, how they are arranged. So as of now, yes, you must study what? The crystal field splitting of d orbitals in octahedral complex and crystal field splitting of d orbitals in tetrahedral complex. See here, for both octahedral and tetrahedral complex, the crystal field studies are different. Why? Because number of ligands are different and the arrangement of the ligands around the central metal atom or the ion is also what? Different. For octahedral, the arrangement is like what? For octahedral, the number of ligands are 6. In the same case, for tetrahedral, the number of ligands are 4. That means the crystal field studies, if you do for these type of complexes, are what? Different in a way. So that crystal field, how the crystal field is working and how the crystal field is studied, it now highly depends upon the number of the ligand and how they are arranged around the what? The central metal atom or the ion. Okay, and the last thing is what? The relative energies of d orbital will be different for different ligands. Yes. So here, according to VBT, we are considering the hybridization of the what? The d orbitals. That is the d orbitals for 1, 2, 3, 4, 5, 6. See, hey, it is only what? 5. Yes, see here. So consider this as a what? A d orbital here. So all these d orbital, dxy, dyz, dzx, dx square minus y square and dz square, all these d orbitals are having what? Same energy. But when we study that d orbital in crystal field, yes, there is what? A different energies are present for these d orbitals. That means that relative energies of d orbital depend upon the what? The ligands again here. So for some kind of ligands, these are the relative energies of the what? D orbital. For another type of ligands, again the relative energy of the d orbital changes. For different ligands, the energies of the d orbital will what? Changes here in crystal field. So that is what it is saying, that relative energies of d orbitals will be different for different ligands. And the last point is very important, that is see here, according to VBT, according to valence bond theory, the experimental value which was calculated for the magnetic momentum were high when compared to theoretical value. Why? Because according to VBT, it was only considering the what? The spin of the electron or the motion of the electron, and it was not considering the what? The orbital motion contribution for the magnetic momentum. But here in crystal field theory exactly explains the what? The magnetic property of the coordination complex. See here, the magnetic property depends upon the what? The splitting of the d orbital. That means here the orbital contribution is also what? Considering not only the what? The contribution by the electrons. Here in C.F.T. we are considering what? The orbitals also. On that note itself, C.F.T. explains in a better way the magnetic property when compared to what? The valence bond theory. Not a better way, exactly magnetic property can be discussed with the help of what? Crystal field theory. See here. So here the orbital means here the orbital contribution is also what? Involving in order to explain the magnetic momentum. See here, the magnetic property depends upon the splitting of the d orbital. And if the splitting is greater here, if the splitting of the d orbital is greater here and lesser will be the unpaired electron. If the splitting of the d electron is greater, that means the decrease in the number of unpaired electron takes place. That means the contribution of the electrons becomes very less. That means what? The magnetic property, the magnetic character or the property also what? Decreases. So the unpaired electron, if you see here, we are considering both orbital as well as the what? The spin of the electron here in order to calculate the magnetic momentum. As we studied earlier itself, in the last video only we discussed the what? The how to calculate the magnetic momentum of a given coordination complex. It is calculated with the help of what? Two things here. One is the what? The magnetic momentum because of the spin of the electron, and another one is the magnetic momentum because of the what? Because of the orbital contribution. So in CFT we are taking both into consideration. The first thing is orbital motion also, that is splitting of the orbital, as well as the what? As well as the unpaired electrons into consideration. So we can study the magnetic property in an exact way in order to what? In order to study the magnetic property of a coordination complex. So these are some of the assumptions of the what? The crystal field theory. The actual crystal field theory depends upon the metal d orbitals. Okay, see here, actual crystal field theory depends upon the what? The metal d orbitals, because the splitting of the what? The d orbital takes place. Which d orbital is undergoing splitting? Which d orbital is moving far away from the ligand? All those things we need to learn in order to study what? The crystal fields. So for our syllabus also we are having what? The orientation of the d orbitals, and also we will study the what? The octahedral complexes, how the crystal field theory can be applied, and for the tetrahedral complex how the crystal field theory is applied. All those things are there for our syllabus also, and we will learn in depth in the next part about the what? The coordination chemistry part 2. See here, once again I am saying these are some of the assumptions, but the actual CFT begins with the help of what? With the help of the splitting of the d orbital and the orientation of the d orbital, and why and how the splitting is taking place with respect to what? The octahedral complexes, with respect to tetrahedral complexes. All those things are there. Yes, we will discuss that in the next part. So those students who have not yet watched any of the videos with respect to what? The coordination chemistry part 2, the links are in the description. Go and watch from part 1, part 2, part 3, and this is the part 4. In the next part we will discuss about the remaining concepts. Okay, thank you.